Okay, in 10G, what we're going to look at is families of functions. So what we're exploring is situations where we've got a polynomial function, but we've got some parameters in there. Okay, so let's have a look at this question here. It actually comes out of the Year 11 textbook, would you believe, and it is excruciatingly challenging. It doesn't specifically say it, but I'm going to use CAS for this question, only because I really want to understand what's going on, and I don't want you guys getting caught up in the algebra, which can be a little bit tricky. I'm going to do this example, plus I've got another example from Ms. Cowan that is also a very good problem. So we'll do two problems for this one. There's only one in your notes, and I'll get you to add the second one in. So here we go with A. So we've got f of x is this, and what we're going to do is find a derivative of f with respect to x, i.e. derive that function. So f dash x equals, and I'm just going to jump on my calc here and clear all and define my function. Okay, just a couple more things to note. They want us to find the derivative, but they've noted that this b value here is always going to be larger than a. And what we got, well, we've got a cubic function. So let's just say that this is a and this is b over here. What's happening there is it's going to have a bounce point here, or it's going to turn on the x-axis at this one here, and it's going to flick back up again and go through B. And note that the cubic is positive, so it's going to start with a positive gradient. So here's what's basically going to happen with this function. It's going to go up to A, turn on it, turn somewhere else, I don't know where, and come back up again. So that's what my function actually looks like. Right, so yeah, it's a good idea just to sort of sketch it to know what you're dealing with. Okay, so I'm going to go over the calculator and diff it. And there's my diffed function. It is 3x squared plus a squared take 4ax take 2bx plus 2ab. If you want to do that by hand, just expand that out and get it to go single term, or use the product rule combined with chain on that to get that. But not really worried about the diffing at the moment. It's the latter questions that I'm really wondering about. Okay, find the coordinates of the stationary points of f. So to do that, we're going to let f dash x equal 0, because remember this is the gradient function, and what you're saying is, hey, can you tell me all the times where its gradient is 0? Okay, so on the calc, I go and do a solve the derivative. When is the derivative equal to 0? For what values of x is it? And here we go. We've got two values. It's going to be, or it's going to occur when x is equal to a. That seems to make sense because there's a stationary point at that intersection with the x-axis there, so that seems to make sense. And the other one occurs down here at this x value, and the x value is a over 3 plus 2b over 3. Right, now this says the coordinates of the stationary points. So what we've got to do is write these as coordinates. Now I think the y value when x is a is going to be 0. And the y value when x is this, well, I wouldn't have a clue. So let's find out. So let's just double check. F of a, got to be 0, got to be, yep. And f of, and we're going to grab that from the calc, throw it into the original function to get our y value. That looks a little bit clunky, and usually if they've thought about the problem in advance, this will simplify down, and it does quite nicely. All right, so this is 4 brackets a take b cubed over 27. So as a coordinate or ordered pair, a comma 0, a plus 2b on 3, comma 4, a take b cubed over 27. So there's our two stationary points. All right, now it says here, show that the stationary point at a comma 0 is always a local maximum. So this is always going to be a local maximum. They want us to show it. So we can't just sort of go view graph top right hand side, obviously max, or say something like all positive cubics have a maximum first. We've got to use some mathematics, and the way we're going to do that is we're going to use a gradient table. Okay, so recall that the gradient table can be set up as follows. What we're going to do is we're going to have top row where we've got values of x. We're going to insert them into the gradient function to find out what gradient they are. And this bottom row here is reserved for a picture of the shape. Okay, so what we do is we choose a point to the left, a point at that point, and a point to the right. Okay, so we're talking about the point A, and what we know is the gradient is going to be 0 at this point. Okay, and that means that we're going to have this here. Now, the way I'm going to show that is I'm going to do f dash a equals 0. Okay, now what I'm going to do is choose a point to the left of A. And A is first, so I'm just going to say that my next point is going to be A take 1. So that's a point to the left of A. So f dash A take 1. So I'm going to go over to my calculator and I'm going to say that, grab the derivative again, so I'm going to diff it. And I'm going to say, can you please substitute x is equal to A take 1 into the derivative function, and it'll throw back this thing here, we'll simp it, and there it is there. So when I sub A take 1 in, the answer is going to be negative 2A plus 2B plus 3. So that's negative 2A plus 2B plus 3. Now, I know that that's a positive number. How do I know that? So here's what I'm going to say in my attempt to show. Negative 2A is always going to be less than 2B, as B is greater than A. So that was what was put into the question. B is greater than A. So I know that this is absolutely going to be the case. Right, so that's my justification about why this is in fact a positive number, because again, when you look at it, negative 2A is always going to be less than 2B. So this negative number is going to be made positive by multiplying by 2B here. So no matter what happens, because we're multiplying by 2 in both instances, this is always going to become positive, and then we just add 3 to that already positive number. So this is guaranteed to be positive, and this is enough justification here to state why you know that that's a positive number. Okay, so now we've got to test a value to the right of A, and this is a little bit tricky. All right, so I remember last year I did this problem on the board and actually made a really calamitous mistake. And what happened was I said, well, we need a point between A and B. So I just did A plus B on 2, which gave me a point in between, slammed that in. And there was a bit of murmuring in the class and I could tell something was going wrong. And the kid said, but what about if the point you chose is actually down here? And the reality was what I had to do is choose a point between this stationary point and this stationary point here. Now this stationary point here occurred when x was equal to a plus 2b all on 3. So what I actually have to do is choose a point between here and here to show that it's got a negative gradient. Okay, and that's what should happen. It should come out negative, but I've just got to grab a value between. So the way I'm going to do that is I'm going to add a to a plus 2b on 3, and then halve the result, and that will give me the value in between. You can find other ways to get values between, but that's the easiest way in my mind to do it, is just to get the midpoint between A and the, or this stationary point and this stationary point. So I'm going to annotate this to say to find point between x equal A and x equal, what was it? A on 3 plus 2B on 3, average 2 points, okay, which is going to be A plus A on 3 plus 2B on 3, all divided by 2. So that is going to be, and I'm just going to get that done on the calculator, and you can see why I've done this on the calc. A plus A on 3 plus 2B on 3 over 2. It's looking pretty ugly. Let's simp it. And that's going to be 2A plus B on 3. So this is going to be the midpoint. So what's going to happen is I'm then going to do F dash 2A plus B on 3 and note the result. So I'm going to sub the midpoint in, and what should happen is when I put it into the derivative, so I've lost it there, so I'm just going to diff it again, and I'm going to do it with x is equal to 2a plus b on 3. I'm going to get that, let's simp that, equals this, negative a take b squared over 3. Now, I know, so I'm just going to fill that in. So this is going to be 2a plus b on 3. This is going to be negative a take b squared on 3. Now, I know that that is a negative number. Now, how do I know that? A take b all squared is always greater than 0. Therefore, negative a take b squared is always going to be less than 0. Okay, and we're dividing a negative number by a positive number there, okay, which means that this, so I'm going to say therefore negative a take b all squared over 3 is less than 0, okay, i.e. it's negative, okay. So once we've got all of that done, we can now conclude safely that this is therefore always a local max. So it's always going to be a local max, no matter what value of A we choose. If the B value is larger than the A value, because of the way these worked out, it's guaranteed that it's always going to be positive, always going to be a local maximum. Okay, so here's the problem from Ms. Cow, and it's in her folder. But so you can pause this and copy it down into your notes, or you can grab it from her folder. I don't really care which one you do. Okay, so the first thing to note is that it's got a restricted domain, 0 to positive infinity, and my function is this, where a is larger than 0. Okay, cool. Determine the intervals on which f is strictly increasing and the intervals where it's strictly increasing function. Strictly decreasing, strictly increasing. Okay, here we go. So what I'm going to do is sketch it. So to sketch it, what I need is the x-intercepts and an idea of where the stationary points are. So what I'm going to do is factorize f of x equals, so let's pull out negative x squared, and we're going to be left with 1 take ax. That means that if f of x is equal to 0, x is going to be 0, and x is going to be 1 on A. So essentially what's going to happen is it's a negative cubic. So negative cubics, remember, start with a negative gradient. So what it will do is swing down to this point here. It's a squared point, which means it's a bounce. So we'd come down, swing in, and it's activated here, so the domain starts here, so it's going to come back up to a stationary point and come back down to another x-intercept of 1 on A. So looking at this, what it's going to do is strictly increase from here to this value here, the value of the stationary point, and it's going to decrease from that stationary point onwards. So our next goal is to find out the value of that stationary point. So all of this is the working out for part A, by the way. So to get the value of the stationary point, what I'm going to do is get f dash x, which is going to be 2x take away 3ax squared. Now I'm going to factorize that. So let's pull out negative x, and that's going to be 3ax take 2. So 0 equals, so I want to find out when the gradient is 0, i.e. can you please grab me the stationary points? X is equal to 0, that's that one there according to the null factor law, and x is equal to 2 on 3a. So the stationary point occurs when x is 2 over 3a. Now I could bang that in to get the y value, but at this stage I don't need to know that because it's going to be strictly decreasing. So it's decreasing over this domain here. So this one here, the answer to this one here is it's going to be from the stationary point, inclusive of the stationary point, 2 over 3a, all the way to positive infinity. It's going to be increasing before that. So starting at 0, because 0 is included, all the way up to 2 over 3a, including the stationary point as well, because any two values chosen over this domain will result in the first value being lower than the second value, inclusive of the stationary point, and the same goes in reverse for this one. Okay, so the next part says find the equation of the tangent to the curve at x is equal to 1 on A. Okay, so for this one here, what we're going to do is we've got a derivative function over here. There's our derivative. Okay, and what we know is that the tangent, we want the tangent, so we're going to get the gradient at x is equal to 1 on A. So to do that, I'm going to do f dash 1 on A. That is, can you please tell me the gradient at this particular point? Okay, so let's sub that in. So that's going to be 2 times 1 on A, that's 2 over A, take away 3A multiplied by 1 on A squared. That's going to be 2 on A, take away 3 on A, I believe. When I multiply them, one of the A's will cancel out, leaving me with negative 1 on A. So at the point 1 over A, we're going to have a gradient of negative 1 on A. Okay, so now what we're going to do is we're going to write this formula in. Y take y1 equals m, x take x1. We're going to use our 2 points. So it's the y value there, which is going to be 0 because it's the x-intercept, equals m, that's what we just worked out, negative 1 over A, brackets x take 1 on A. The x value at that point is 1 on A. So that's going to be y equals negative 1 on A x take 1 on A. We could probably leave it like that. That's the equation. Yeah, we're pretty safe in actually leaving it like that, but I don't know. Negative x on A, take away, or plus rather, 1 over A squared. So there's our equation of the tangent. Normal is going to be very similar. So we know that the gradient of the tangent at that point is negative 1 on A. So therefore, if M1 has a gradient of -1 on A, M2 will be the negative reciprocal of that, which will be that flipped and negated. It's going to be A. So let's redo this. We're going to have Y take Y1 equals M, X take X1, Y take 0 equals M, which in this case is A, X take 1 on A. Y equals AX, take away A on A, Y equals AX, take 1. All right, so there's our equation of the normal at that point. All right, what is the range of f? Okay, well, what we can see is it's going to be negative infinity is the lowest value because that's where it continues, all the way up to this point here, which is going to be the local maximum and also the absolute maximum. And that can be acquired by doing f of 2 over 3a. So whatever that value is, that's the x value where the turning point or stationary point occurs. So if I insert that in, I'm going to get my y value. So let's do that. I'm going to do it up the top here because I need to see this function, but you guys hopefully are a little bit more organized on your page. So that's going to be f of 2 over 3a is equal to 2 over 3a all squared. Take away a lots of 2 over 3a cubed. That's 4 over 9a squared. Take away a lots of 8 over 27a cubed. That equals 4 over 9a squared. Take away 8 over 27a squared. Could probably leave it like that, but let's tidy up after ourselves. So I'm going to multiply by 3, which is 27 over a squared, take away 8 over 27a squared, which is 4 over 27a squared. All right, so that is f of 2 over 3a. So our range is going to be negative infinity to 4 over 27a squared. All right, so there it is, another applications problem with parameters. Not easy stuff, this. We're used to getting single digits or numbers as answers, but remember with parameters in there, it all depends on what the value of that parameter is.